Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Mitch Begelman, who is Professor of Astrophysical and Planetary Sciences at the University of Colorado Boulder and a Fellow of the JILA, a Joint Research Institute of the University of Colorado and the National Institute of Standards and Technology. He studies aspects of how black holes form, grow, and interact with their surroundings from a theoretical perspective. Welcome, Mitch.
Hello.
Yeah, thanks for doing this. So I want to start with one of your papers on black holes from 2006 entitled Formation of Supermassive Black Holes by Direct Collapse in Pre-galactic Halos, in which you say we describe a mechanism by which supermassive black holes can form directly in the nuclei of photogalaxies without the need for seed black holes left over from early star formation. Before we get into this, Mitch, black holes is really sort of a discontinuity in space-time. When a lot of mass gets concentrated in short spaces, essentially we have a discontinuity that we can't quite understand. But there are different masses of these black holes, and some of them are what you call supermassive black holes that tend to be at the center of galaxies, right?
Yes, yeah.
So there is one, I believe, at the center of the Milky Way galaxy, our own galaxy. And I guess there are a lot of theories around how they are formed. So this is one of the hypotheses of how they might have formed.
Yes, yeah. Black holes are places where you have so much mass concentrated in such a small region that the gravity of that mass is so strong that nothing can escape it once it gets trapped. Yeah. In fact, they're even weirder than you think. They're not really necessarily made out of matter. They are places where Einstein tells us that gravity is really the result of space-time curvature, and they're places where the curvature of space-time is so kinked up that in fact it kind of feeds on itself, and kind of space gets closed in on itself. So in theory, in fact, you could produce a black hole without any mass, but in practice, I mean, just by curving space-time. But in order to get space-time kinked up enough, in practice in the universe, we know that this happens when large amounts of mass collapse to a small volume. Now, the nearest black holes to us, and by near I mean probably within a few hundred light years, so near by my standards, not necessarily by that of many of the listeners, those result from the collapse of massive stars that run out of nuclear fuel and just can't hold themselves up against gravity. But we also know that there is a second class of black holes that seems to, in which there seems to be one at the center of every large galaxy, and there's still a lot of controversy about how those could have formed. These black holes are responsible for some dramatic phenomena such as quasars, which are very luminous objects, usually found in quite distant places.
Yeah, so when we think about black holes, we think about the event horizon. And so what you're saying is that the event horizon is sort of a boundary. Once you cross that, not even light can escape. But it doesn't really mean that's the size of the black hole, right? It just sort of a concept, really.
Yeah, well, it's the point of no return. It's the surface beyond which anything that crosses it is lost. So it can no longer communicate with the universe outside.
And so there was some, sorry, Mitch, I know there was some excitement about this Event Horizon Telescope. And I don't know, either the pictures that they produced are actual pictures or some simulated thing.
Well, they're basically images made using a set of radio telescopes. Now, a radio telescope doesn't work in the way where you can look through an eyepiece and you see an image. It's what it does is it takes signals that are received by many different pairs of radio dishes located with large separations, and what you do is you sort of reconstruct the appearance of the object that's sending radio waves to these radio telescopes by comparing the signals that any pair of them receives at a given time. The procedure is called interferometry, and it's used in many different branches of physics. But given that we understand how to reconstruct the images from an interferometer, this really is an image of the light that's passing close to a black hole. Yes.
And it sort of looks like what we imagined it looked like, right?
Yep, looks like a hole.
Looks like a hole. And, it is an amazing thing because I think the whole concept started from theory, right? Einstein sort of hypothesized such a thing could exist.
Yes. Now, I should emphasize that what the Event Horizon Telescope has imaged is not really the size of the event horizon, because the way light is bent close to the event horizon, you don't really expect to see an image of right outside the event horizon itself. What we're seeing is really called the photon ring. And so what it indicates is that there is gas sort of surrounding this black hole, but in particular, there's gas behind the black hole. And some of that light is going in our general direction. And what we're seeing is the way in which the space-time curvature has contoured that light into a ring. And the size of the ring on the sky, taking into account how far away this black hole is, it's about 50 million light years away. Given the distance, the size of this ring is a few times the size of the event horizon. So we're basically seeing sort of a silhouette kind of offset a little bit from where the actual location of the event horizon would be.
Okay. And that picture that sort of gotten famous, is that the Milky Way supermassive black hole?
No, that's a black hole in the center of a galaxy called M87, which is located in the direction of the constellation Virgo. That galaxy is 50 million light years away. The center of the Milky Way is only 25,000 light years away, so it's less than 1,000th the distance. The reason we can image the black hole in M87 is because it's gigantic. Its mass is more than 1,000 times that of the mass in the center of the Milky Way, and that is partly reflects the fact that M87 is a much larger galaxy than our Milky Way.
And I would imagine if we are trying to image the Milky Way's supermassive black hole, there'll be a lot more interference, right? There'll be a lot more noise that we'll pick up.
In the Milky Way's black hole, there's a little bit of a difficulty in getting a good image, and that's because the Milky Way's black hole is so much smaller than the one in M87. The gas around it is varying much more quickly, simply because it's a smaller scale. To construct an image using interferometry takes about really takes about 10 or 12 hours. And the Milky Way black hole is kind of flickering on and off over that time. So it's very difficult to get a good steady image. I think we're very close to that, and I wouldn't be surprised if there's an announcement pretty soon, within the next few months or so. But we don't quite have a good image there yet.
And sometimes black holes are more active. Sometimes they just sleep for a long time. And the Milky Way's supermassive black hole is sort of passive right now, isn't it?
It's very quiet. Yes.
Yeah.
It's there's not much happening. Not much gas is swirling around it and falling in right now. Yeah.
Right. And so, like you mentioned, you don't necessarily need a lot of mass to create a black hole. It's really a kink in the space-time fabric. But typically, black holes are formed by mass getting together, and then it starts attracting more mass. It sort of goes on a runaway process. You want to talk a bit about, the way that you're thinking about the mechanism that you describe in this paper?
Yeah, to form these giant black holes in the centers of galaxies, you need to bring together at least a few million solar masses. That's what happened in the center of the Milky Way. In the case of M87 and other really huge galaxies, it's more like a billion solar masses. And it turns out that it's not obvious how to collect such huge amounts of material in a small enough place for it to collapse to form a black hole. In the case of the stellar mass black holes, the ones that result from the collapse of stars, we know that there are stars which are a few tens or even 100 times the mass of the sun, and that when they run out of nuclear fuel, they will just spontaneously collapse under their own gravity. It's not so simple to figure out how you form a supermassive black hole, because there are no obvious structures in the universe like stars that have masses of millions of solar masses. In other words, if gas under ordinary circumstances kind of drifted in towards the central region of a galaxy, we wouldn't expect it to all collect in the center in a small enough region to form a black hole. We would expect almost all of that gas to kind of condense into stars on the way in and never quite get to the center. So that led to the earliest ideas of how you might form these supermassive black holes, is that you just form a lot of stellar mass black holes by taking the stars that form in the center of a galaxy, wait till they form black holes, and then somehow either merge those black holes together through collisions, or just wait until they accumulate enough mass, because of course black holes can grow in mass as they swallow things that fall into them. The problems with that are, one, that it's really hard to collide individual black holes because they're pretty small. We say that black holes swallow everything, but to get swallowed by a black hole, you have to get pretty close to it. You actually have to get pretty close to the event horizon. So it's very hard to see how even a collection of stellar mass black holes would merge at a fast enough rate to build up these million to billion solar mass black holes. Even swallowing gas, there are some limiting factors in how fast an individual black hole can swallow gas. I mean, once the stuff gets really close to the horizon, okay, it goes in.
Yeah.
But in order to get close to the horizon, there's all kinds of things that can get in the way. For example, the gas that's approaching the horizon gets compressed, it heats up. Magnetic fields that are present everywhere in the universe build up, and these can actually shoot the gas back out before it even reaches the black hole. So we kind of have a slogan in this business that black holes are fussy eaters, and it's really something that seems to be true. It's not that easy to feed a black hole a lot of material. So the ideas that are most obvious about how to create these supermassive black holes don't seem to have a lot of a high likelihood of working. An alternate set of ideas, which I've been involved in, and that's the subject of this 2006 paper, is that you can get around this if somehow you can get gas, a huge amount of gas falling into the center of the galaxy all at once. and then it just builds up to the point where you just can't. It just can't hold itself up, and it forms a quite large, not quite supermassive, but a quite large black hole very early, maybe of a few thousand to a few 100,000 times the mass of the sun. Once you do that, it's much easier to understand how such a black hole can grow.
So Mitch, if I understand this correctly, it's sort of difficult to build a supermassive black hole incrementally.
Mm-hmm.
We understand the sort of the smaller ones, sudden collapse in a supernova or something like that. That physics is well understood. But the idea that you can just sit there and keep eating and become a supermassive black hole seems to create some issues, right?
Yeah.
Yeah.
Yeah, it's difficult to get a high enough rate of mass continuing to build the black hole to build these supermassive black holes in a short enough time. We do actually know something about how long it took to build these supermassive black holes, because quasars, which probably many people have heard of, what quasars are black holes that are swallowing matter at a pretty high rate, and the matter is getting hot and producing a lot of energy, which we can see with telescopes.
And they're very early in time, right? Maybe a billion.
They formed very early in the history of the universe.
Yeah.
So some very luminous quasars, which means some huge black holes, were already formed less than 1 billion years after the Big Bang. And to form a black hole that massive so early in the universe requires a huge rate of swallowing. So it's very hard to understand how you could have done this starting with very small seeds, the mass of a few times the mass of the sun. You really need to start with a large initial collapse. And then once you have that, it's much easier to build up these very massive black holes pretty quickly so that quasars can start.
Yeah, so what does the demographics tell us, Mitch? So if you look at the size of the black holes, do we see sort of small ones and then we see really big ones and maybe a gap in between? Or what do you see from a perspective?
Well, we see a pretty big range of black hole masses.
Yeah.
And there is a very good correlation between the mass of the black hole and the mass of the galaxy that hosts it. In fact, they seem to go roughly in proportion. So it's not surprising, given what we understand about the demographics, it's not surprising that the Milky Way only has a few million solar mass black hole at the center, whereas M87 has a few billion. M87 is a galaxy that's about 1,000 times bigger than the Milky Way.
Yeah.
Now, we can extrapolate this down to galaxies that are even smaller than the Milky Way, and we find that this correlation seems to go down to about 100,000 times the mass of the sun. We don't really know what happens below that, but so far, there does seem to be some kind of a gap between these stellar mass black holes and the supermassive black holes. There is some evidence that there may be some black holes in the range of a few hundred times the mass of the sun.
Yeah.
There's some evidence recently from the LIGO gravitational wave detector, for example. But we don't really see a lot of evidence for intermediate mass black holes. And right now there's a big debate where people are waiting to see if there's a continuous distribution of black holes, suggesting that maybe some of these stellar mass black holes did grow by accumulating from these small seeds, or whether there really is a gap, which would indicate two completely different mechanisms for forming them.
Right. So the current observation is that we have sort of a gap. And so this hypothesis that the supermassive black holes are formed by a different mechanism altogether seems like more intuitive, right? Is that our current best understanding?
I would say there's a split in the community. There's two different camps.
Yeah.
To me, it seems more intuitive that black holes, the seeds of these supermassive black holes, formed from some kind of a direct collapse of gas, started, giving you maybe a few thousand or 100,000 solar masses, and then going up from there. But there is still a lot of work aimed at seeing whether the formation of these, the growth of these stellar mass black holes might also be viable. And it's quite possible that both mechanisms contributed. We're just not sure yet.
Yeah. Without knowing a lot about it, Mitch, when I thought about M87, a billion solar masses, Milky Way, a million solar masses, it seems like there's clearly a relationship between the size of the galaxy and the size of the black hole. I would have thought that sort of implies that the black hole in a larger galaxy had more opportunity to eat, but that's not the case, right?
Yeah, well, I think that that what you're seeing is evidence that the assembly of the galaxy was also responsible for the assembly of the black hole. But we do have a chicken and egg problem here. We're not sure whether black holes formed before the main galaxy condensed, or whether the galaxy formed first and the black hole formed out of the debris that was left over. That's still very much an open question.
Right.
The way we think galaxies formed is that they form from the hierarchical mergers of smaller galaxies. So the way it works is you form the first thing we might call a galaxy would be maybe 1,000th the mass of the Milky Way, and it's quite likely that the seed of that eventually became our black hole formed in one of those precursor galaxies that was much smaller, and then as the different pieces assembled, this precursor black hole sank to the center and then grew maybe by a factor of 100 to become the million solar mass black hole we've detected today.
Okay, and so you say here the mechanisms you're talking about, supermassive black holes can form directly in the nuclei of protogalaxies. So protogalaxies don't imply small galaxies, right? It's just early galaxies.
Yes, but we think that the current day galaxies that we see formed from much smaller galaxies at earlier times. So
right.
We're not exactly sure when when most of the supermassive black holes formed. We know a few of them formed very early, but that's probably not the typical ones. But the seeds of the supermassive black holes that formed that led to the giant black holes in M87 and the Milky Way today could well have formed initially in fragments that were much smaller than the final galaxy. So, in other words, the picture that we proposed in our 2006 paper, which is just one possible way of doing this, is that you form your first 10,000 or maybe 100,000 solar mass black hole in a galaxy that's only 1/1000th the size of the Milky Way.
Yeah.
And then you merge 1,000 of these together, each of which may have had a black hole in it, or maybe only 1 in 1,000 had a black hole. You merge them all together, and those 1,000 pieces, which make up today's Milky Way, would have also a seed leading to the Milky Way's million solar mass black hole.
And so, let me know if I understand this correctly, Mitch. So, once you get to 100,000 solar mass black hole, then you can sort of go the kind of a Lego process. Meaning when two galaxies merge, the black holes in them dance around for a while and ultimately merge. And so using that type of a process, you can get to very large black holes.
Some of the growth of the black holes probably was due to mergers, but also a 100,000 solar mass black hole has a lot less trouble swallowing a huge amount of matter than a 10 or 100 solar mass black hole. So we also exploit the fact that if you start with a much larger seed, then the subsequent growth to get a billion or million or a billion solar masses is not that difficult. And if you track the relative prevalence of mergers of black holes versus the likelihood that black holes just swallowed a lot of gas, probably the gas wins. So you may have had mergers being important in driving black hole masses from 100,000 to perhaps a few million. But to get much above a million, I think most of us have concluded that just swallowing gas is probably the way to go. And we see evidence of that process happening because we know that at various points in galactic history, there are episodes when black holes are swallowing a lot of matter, and those episodes are visible as quasars.
So when we look back to quasars, maybe 1 billion years from the Big Bang, how big are those things?
Well, funny you should ask. This week at the meeting of the American Astronomical Society, it was announced that there is a new record holder for early and massive black hole.
Yeah.
And the black hole was observed at what we say is a redshift of 7.6, which means about 650 million years after the Big Bang. The mass of this black hole is just under 2 billion solar masses, so it's actually not the largest black hole. The M87 black hole is 6 billion.
Right.
But to form a 2 billion solar mass black hole, only 650 million years after the Big Bang is quite a feat. So it actually does challenge some of the theories of black hole seed formation even more than they've been challenged in the past.
So does the prevalence of quasars early in the history of the universe, does that sort of settle the chicken and egg problem? Could we actually say it's more likely that the supermassive black holes came first and then galaxy formed around it?
Well, you might think that, except these black holes that formed really early, these really early quasars, are extremely rare.
Oh.
And so they probably formed in exceptional regions where there is evidence. We do see evidence that there's a huge galaxy surrounding this black hole. So we do know that there are big galaxies that formed this early in the universe. But most of the black hole formation probably occurred much later, and it probably is hard to disentangle whether it precedes or follows or is simultaneous with the development of the galaxy, the host galaxy. So it's a closely run thing. It's really hard to separate which came first. I think there is some evidence that some black hole formation formed before most of the stars in their host galaxies might have been created, but I don't think the evidence is really that firm yet.
Right. Okay. We'll take a quick break, Mitch. When we come back, we'll talk more about black holes.
Okay.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So, Mitch, we are back. We're talking about black holes, which is sort of a kink in space-time. And there is a good understanding of how they form when they are small enough to understand them, maybe a few solar masses. But at the center of the galaxies, we have this variety called supermassive black holes. And the mechanisms used to describe the formation of smaller ones don't quite work for them. But you had a hypothesis around this, how that might have happened. I want to go into another paper that you have entitled Quasi-stars, accreting black holes inside massive envelopes. Mm-hmm. You say that we study the structure and evolution of quasi-stars, accreting black holes embedded with massive hydrostatic gaseous envelopes. These configurations may model the early growth of supermassive black hole seeds. Mm-hmm. Now, this sounds to me, without knowing a lot about it, this sounds to me is more in the feeding type mechanism, is it?
Yes, yeah. So this is after you formed that first seed. Through the direct collapse of a cloud of infalling gas.
Okay,
yeah.
So this is after you get to that 1,000, 10,000 solar masses. You already have a pretty big one. And the question is, how does that grow to the million solar masses or a billion solar mass black hole we see at the center of galaxies?
Right. So the basic idea is one of the problems with growing a black hole really quickly is there is a kind of a sense that there should be a growth limit. And the reason for this is that the gas that's about to fall into a black hole gets very hot. It releases a lot of radiation. That radiation tries to stream out while it still can, because the gas is still outside the horizon. Well, streaming radiation escaping from some source actually exerts pressure.
Yeah.
So, I mean, even the radiation from a light bulb exerts a little bit of pressure, which is so small that you can't feel it. But if you're talking about a quasar, the amount of pressure that can be exerted can actually exceed the inward force of gravity. So one of the limiting factors that makes it a bit hard to grow a black hole infinitely rapidly is this back reaction of the radiation. It's called the Eddington limit, named after a British astrophysicist from about 100 years ago. That provides that if you say that determines the limiting growth rate, that provides a limit to how quickly a black hole can go from 100,000 to maybe 10 million, 100 million, or even a billion solar masses. And that's one of the things, the factors that creates a problem for understanding how quasars could have turned on so soon after the Big Bang. Well, the quasi-star idea exploits the fact that if a black hole seed forms from this collapse, not all the gas is going to collapse simultaneously to form a black hole. There's going to be a remnant of quite a massive remnant of gas left behind. And that's simply because the gas that's trying to collapse has a little bit of spin, and the spin inhibits the gas from collapsing all at once. We estimated what this process might look like, and interestingly, the remnant of gas that's left behind actually turns out to be much more massive than the black hole that collapsed initially. And so the quasi-star idea is that you have a black hole collapsing at the center of a very massive cloud, and the gas from the very massive cloud is continuing to pile into the black hole. Well, now the radiation pressure that's exerted as the gas heats up and the radiation flows out, that radiation has to contend with a much larger gravitational field further out from the black hole. And so we're basically using this envelope to counteract the effects of radiation. And that allows the black hole to swallow matter at a rate that might be even 10 or 100 times higher, allowing the black hole to grow to huge masses faster than initial predictions suggested. So that was the quasi-star idea. Now, the interesting thing about this is we then thought about what such a system would look like. What would it look like if you had a black hole at the center of a very massive cloud being puffed up by this escaping radiation, but not being dispersed because the cloud is so massive? Well, it turns out that such an object should look pretty much like a red giant. So we suggested that these very rapidly growing black holes early in the universe might actually not look like quasars, but might look like red giants. In other words, they would be very luminous, but the radiation would not look like a lot of X-rays, which is what you have in a quasar. Ultraviolet radiation might be more like red.
Right.
So this is just one idea for how what the rapid growth phase of a black hole might look like, and one of the possibilities that this sort of things might be detectable with the James Webb Space Telescope, for example, which we hope will be launched within a year, but its launch date has been within a year for the last 5 or 6 years. So we're still optimistic. Hopefully, it will be launched before 2022.
That is the space agency?
I'm sorry, could you repeat that?
Is that European Space Agency?
No, James Webb is a NASA mission.
NASA mission. Okay.
So it's the next gigantic space telescope, and it will be a 6-meter mirror, whereas the Hubble Space Telescope is a 2.4 meter mirror, and it is particularly optimized for far infrared radiation.
Okay, so am I thinking about this correctly, Mitch? So the envelope, so there is a black hole that is already formed by the general process to get to 1,000 solar masses or so, but it's sitting in a very large envelope of gas.
Yeah.
And so, in some sense, it's not an incremental process. That because of the gas, you can have another big sort of contraction, if that's the right term, at the black hole. So it can go from 1,000 to 10,000 to 100,000, and not build up incrementally. Is that the way to think about it?
That's a good way to think about it. Now, you probably can't get beyond maybe a few million solar masses, because eventually you'll blow away the envelope. There are some restrictions on how much more massive the envelope has to be than the black hole in order for this to work, and there are some other limitations. But this might be a very helpful intermediate stage in explaining how you could get very rapid growth of the black hole.
And you mentioned they might look like red giants. So the red giants that we see today, they are truly red giants, right? Are they something like this in some cases?
Well, the red giants we see today are just normal mass stars.
Yeah.
And the thing that makes this look like a red giant is the structure of the energy source. So what's happening here is that it's a red giant that's being puffed up and powered by the intense release of energy very close to a very small object in its center. Now, red giants that we see today are stars where the core of the star has contracted to something that's not much bigger than the Earth, and nuclear reactions are just going on in a shell around that star. So it's kind of geometrically analogous to this black hole envelope situation, except in the case of a normal red giant that we see in the Milky Way galaxy, we're talking about something with just a mass of the sun, or a couple times the mass of the sun, with a very compact core and intense nuclear reactions around that core. The case of a quasi-star, we're seeing a much more massive envelope, with the energy source being the gas that's just outside the black hole, sort of in a shell. So it's kind of analogous to the red giant situation. And it turns out it's that geometric structure of energy being released in a relatively thin shell that puffs up the envelope and makes it look like a red giant. So it's kind of a very interesting analogy that spans, a factor of thousands or tens of thousands in mass, but two completely different processes giving you kind of analogous structures.
And how far back do you think James Webb and others need to look to find something like this?
We estimate that this kind of process probably did not become relevant until maybe 400 or 500 million years after the Big Bang. May have peaked about 900 million years after the Big Bang, maybe 1 billion years after the Big Bang, and then declined very quickly after that because there was simply not enough gas falling into the center of the galaxy. In other words, at some point, all the gas that has not sort of condensed on the black hole is going to form stars, and then it's out of the game. So we think that the best place to look is sort of a redshift between about 15 and 6.
Okay.
Yeah. So that's about 500 million to about 1 billion years after the Big Bang.
Yeah, still pretty early. Pretty early in the evolution.
Yeah. So, and this would be before most large galaxies like the Milky Way formed. So this would still be a process occurring in a fragment proto-galaxy that hasn't quite found all of its neighbors yet, and has not quite formed the final galaxy.
So they're sort of timeline-wise, they're sort of in the same zone as quasars then.
Well, it's in the same zone as these very extreme quasars, like the one that was announced this week. But actually, most quasar activity occurred later,
Oh,
at a redshift of 3. That 2 to 3 is the peak of the quasar era, and that's actually a couple of billion years after the Big Bang.
okay. I want to go into another paper you have, Evolution of Supermassive Stars,
Mhm.
Pathway to Black Hole Formation. So this is sort of another mechanism for black hole formation. You want to talk a bit about that?
Yeah. So actually, this is a phase that we think is probably earlier than the quasi-star phase. So this is actually the question of, if you do have this gas that's all coming together and it's going to ultimately form a seed black hole, how does it reach the point where it actually collapses to a black hole? And so what we did was we just assumed that matter was coming into the center of the galaxy at a certain rate, which we can actually estimate pretty well. And we asked what happened to that gas. And the question was, does it just sort of accumulate, boom, goes into a black hole? And the answer is probably not. And the reason is that the gas that's accumulating, as it kind of piles in on the pre-existing accumulation of gas, it gets hotter and hotter at the center. In other words, you're just feeling the center is experiencing higher and higher pressure, and that not only compresses it to higher densities, but most importantly, it drives it to higher and higher temperatures. Well, what happens when you take a gas and bring it to a high enough temperature is that thermonuclear reactions start. And so what I realized was that probably this is a way, before you get a collapse to a black hole, you probably form something that's like a supermassive star. In other words, something somewhat like a star in that it's supported by nuclear burning, but it's thousands or even tens of thousands of solar masses. So what this paper is about is kind of a study of what these stars would be like.
Yeah, it just mind-boggling. It's difficult to imagine a star to a sort of a million solar masses or something along those
Yeah.
lines. And this is early, so all the nuclear burning is pure burning, hydrogen to helium, right?
Well, yes, very interesting aspect to that. The process by which the sun releases nuclear energy is called the proton-proton chain. Okay, so you basically, through a fairly complicated series of nuclear reactions, you basically just add protons together and eventually you get a bunch of helium. That process actually cannot produce enough energy to stop the collapse. Because the masses of these stars are so high, you actually need a very large nuclear output to support such a star against collapse. And so if all we had was the proton-proton chain, these things would just collapse straight to black holes. What you need is a reaction called the CNO cycle, which is like it's a catalyzed reaction. It's like catalysis in chemistry, where you actually, in order for this thermonuclear reaction sequence to go, you actually need nuclei of carbon, nitrogen, or oxygen atoms in order for the process to be catalyzed. Now, there is no carbon, nitrogen, or oxygen right after the Big Bang.
Right.
The universe is entirely hydrogen and helium, with some other traces which are not important for this. So actually, you need a little bit of oxygen or carbon or nitrogen for this to happen. And so you need to ask where that tiny contamination of, say, carbon is going to come from. And so it's possible that this process won't actually happen. But it seems quite likely that there will be trace amounts of carbon by this point for two reasons. One is, even though we're saying that this process occurred right after, pretty soon after the Big Bang, it's still about a few 100 million years after the Big Bang. Now, much earlier than that, only maybe 100 million years after the Big Bang, or even earlier, stars started to form. And so stars rapidly synthesize carbon. And as soon as those stars go supernova, that carbon gets into the environment. And so even a tiny mixture of carbon, 1 part in 10 to the 8 or something like that, 1 part in 100 million, is enough to get the CNO cycle going. The other thing is that you can fuse helium to form carbon directly.
Yeah.
That's called the triple alpha process. And that actually becomes important if the temperature gets high enough. And so the other thing that could have happened is that as this core gets hotter and hotter, it fuses enough helium to give you this contamination by carbon. But once you get a tiny fraction of carbon, then the CNO cycle dominates the thermonuclear reaction. It creates helium from hydrogen. You don't burn the carbon in this process. And that would stop the collapse for about 1 million years.
Right.
And so it seems that there's a hiatus in forming a black hole, even by direct collapse, due to this big accumulating mass of gas forming a kind of a supermassive star.
So it sounds like if you have a small amount of carbon, it becomes sort of self-sustaining.
Yeah.
Because you produce a little bit and you produce a lot more energy with it as a catalyst, and that keeps the infrastructure in balance. And so could we actually compute or simulate what composition is needed for that process to be stable?
Yeah, that has been done. There has been some subsequent work on working out the details of this thing. And in fact, the idea of these supermassive stars was first proposed back in the 1960s by Fred Hoyle and Willie Fowler. So it's been around for a long time. In fact, it was one of the early proposals for what powered quasars before people realized that these supermassive black holes were real.
Right. I want to finish up with one of your recent papers, which is sort of related, but also in a different area. So, strongly magnetized accretion risks, structure and accretion from global magnetohydrodynamic simulations.
Okay.
So the magnetic aspects of accretion, it plays a big role in both formation of black holes and all of that, right? So is it going into that?
Yes. Well, we've known for some time that magnetic fields are absolutely essential for all black hole astrophysics, because as I said near the beginning, black holes are really small targets. If you just rely on stuff flying around in space and happening to hit a black hole, you're not going to have black holes swallowing a lot of matter.
Yeah.
And so in order for black holes to actually swallow substantial amounts of matter, the matter has to give up its swirling motion around the black hole. It's what we call its angular momentum. And the most likely candidate for allowing that angular momentum transfer to happen is the action of magnetic fields, which kind of behave like a cross between a kind of a spring and a rubber band. It kind of there are magnetic fields embedded in all the hot gas that we know of out in space, including the gas that's swirling around a black hole. And as the gas swirls, there's kind of this snapping action of magnetic fields that kind of gradually reduces its spin and allows it to eventually reach the black hole and enter it. And so we've known that that's the main mechanism allowing accretion, allowing black holes to swallow gas for about 3 or 4 decades now. But one question that's never been resolved is exactly what configuration does this magnetic field attain in this swirling gas, and in particular, how strong does the magnetic field get?
Yeah.
So people have kind of tried to work backwards, saying how strong does the magnetic field have to be in order to do this? But we haven't really gotten a satisfactory answer as to what the theory really predicts about how strong these magnetic fields can be. Well, as we are able to do better and better simulations of these magnetic fluid processes, the picture that's begun to emerge is that these magnetic fields can become much stronger than we expected.
Yeah.
And so if that actually happens, they are going to have a big impact on how gas actually swirls into the black hole. And in fact, what I suspect is that these strong magnetic fields can explain a lot of things that so far have been hard to understand about what we observe when we observe a black hole that's swallowing matter. So that's what this paper is about.
So is there some sort of a critical threshold, Mitch? So I'm just thinking that if you get to some level of magnetic pressure, then you are able to get the gas in. Would that increase the magnetic field of the black hole, and it can take more gas in? Does it go like that, or?
Yeah, there seems to be some kind of a bootstrap effect. So basically what's happening is that as the gas swirls around the black hole, it stretches the magnetic field into a circular pattern around the black hole as well.
Yeah.
And the idea is that, like radiation, magnetic fields also exert pressure. And so the idea is that you're basically twisting the spring or this rubber band so much that it's getting stronger, it's getting more and more resilient. And so it begins to puff this gas up around the black hole. And although you might think that that puffing up is kind of resisting the black hole swallowing matter, what actually seems to be the case is that it probably helps the black hole swallow matter.
Okay. And so this mechanism then, again, going back to the different mechanisms that we discussed by which black holes form, this is sort of that incremental process that how does the gas get into the black hole question, right?
Yeah.
Yeah. So,
well, it's to some extent it's an incremental process, but to another extent it's actually an unstable process because what seems to be the case is that if you have only a small amount of magnetic field present initially, you end up with a small amount of magnetic field. If you, on the other hand, raise that, you have a larger amount of magnetic field initially because of the environmental conditions. Maybe you're trying to swallow gas that started out with a larger magnetic field. There seems to be a threshold, and beyond that threshold, the magnetic field that you end up with grows by a large amount. So a small field goes to a small field, but a moderate field goes to a huge field.
And the magnetic field is sort of the property of the black hole. You cannot have a black hole without magnetic field.
Oh yes, sure you can. The magnetic field in general is a property of the gas between the stars and between the black holes, and in fact every star has its own magnetic field. So magnetic fields are kind of an ambient property of the universe. If you take a black hole and just let it sit there, it will not develop a magnetic field unless there is gas that is pushing in on it that has a magnetic field, and then some of that magnetic field will appear to be emerging from the black hole. Actually, what you're seeing is the distortion of an external magnetic field by the black hole. So black holes themselves do not have intrinsic fields. In fact, we call a magnetic field around a black hole, we call it hair. And there's kind of this theorem that usually has the slogan, black holes have no hair.
Right.
So a black hole by itself doesn't have its own magnetic field, but a magnetic field imposed on a black hole will interact with it particularly if the black hole is spinning.
Does this is this useful to think about why black holes go quiet and then become suddenly active?
Well, yes. One of the interactions of a magnetic field with a spinning black hole is that some of the spin of the black hole can be extracted and used to power a jet.
Yeah.
And so we see these very powerful jets which are emerging from the regions around black holes. One of the leading theories for how that's those jets are created is that they're actually extracting the energy from the spin of the black hole.
Clearly not practical, but presumably we can get energy from a black hole if we can get hold of one, right?
Oh yes. This is the idea of a Dyson sphere.
Yeah, and there was some talk about the
famous
Planet 9 too.
Yeah.
Right. So in conclusion, Mitch, you look forward 5 years. I know what is the telescope that you mentioned, James Webb, is going up. There are a few other missions planned by NASA and others. Where do you think we will be in these types of questions 5 years from now?
Well, I'm hoping that we will have a much clearer idea of how and when those first supermassive black holes got going. We should, with the new telescopes, we should be getting pretty close to really seeing all aspects of the era of galaxy formation and beyond, including the development of these first black holes. I also think we're going to see a lot more exciting results from not only the Event Horizon Telescope, but other projects that are able to really go right down very close to the horizon. And one of the things I'm particularly excited about is that the next generation of results from the Event Horizon Telescope may actually show us the jet in the process of formation. Right now we can see the photon ring, but the Event Horizon Telescope is not quite sensitive enough to see how the jet might connect to that gas that's swirling around the black hole that we kind of see the glow of now.
Yeah, I mean, these pictures really capture the imagination of the public. I never thought I could see something like that. And
neither did I.
Yeah.
A lot of us were kind of scared. We thought it was a great thing to try, but we were not that optimistic that we would see something like this. This is like the best of all possible things we could have expected to see from it.
Right. Excellent. Yeah, thanks so much, Mitch, for spending time with me. This has been
great. Thank you.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.